we get to the overloader operator. We don't expend any time in this class to go over this. This operator plus is a method that can be used to operate on the invoking class objects and instances. This usually deserve maybe half a lecture, but in this class, I decided not to do it. You can create something that looks like a arithmetic operators, but they are really a method that can be invoked on the type that is left operand is on, is of, right? Let's say if this A is of struct product, then this operator plus, which looks like A plus B, this plus right here, it's actually a method that is operated on, that is a part of A, this instance of product, right? So in other words, this plus is actually a method inside a product. That's what this is. Okay, so you don't really see this in other languages because this is really confusing. But just in case you're wondering how in the world can you do A plus B equals AB, right? Only in C++ or maybe in Java too. So this plus turns out to be a method that is of type string. So this string class has this plus operator plus method in it that allows you to do it. Anyway, so this thing is static polymorphism. Okay. The reason why this is static means that this logic is baked in at compile time. Okay, not runtime. Hence the word static. Okay, static actually has a lot of different meanings, meaning this is the of the class, not of the instance. But then again, I divulge in out of scope for this discussion. Just remember your operator plus is in your overloaded operator is a static polymorphism. Okay, so right now let's look at dynamic polymorphism. This is something that happens only at runtime, not at compile time. So what you're seeing is it's an elementary definition of a point class. This point class has two attributes and one method associated with it, both protected. They could be inherited. Both X and Y could be inherited directly by circle if you make circle to be the child of point. Okay, so if we're to draw this on a class diagram using UML, right, Unified Model Language, then you draw this. This is the inheritance pattern. Inherit. Okay, circle. Then, oh, I spell it wrong. Do it again. Then you can kind of see the circle is a, okay, inheritance point. Circle inherits everything, including the protected and public member of point. So this means that circle has what's called R in it, area, method, also X and Y, and also area from point. Okay, point is a pointer. So both areas, but mainly this area, which is the circles area right here. So that's what this inheritance means. And sometimes we call this subclassing. Okay, this means that you're subclassing point into a different variable or different instance. And the subclass is called circle. Point is called superclass. So the act of inheriting a circle from point is what we call subclassing. Okay, subclassing. All right, so we heard a lot about these terminologies. Let's move on. This basically says circle has everything that this point instance has, right? Now we're talking about instance, not class anymore, right? Because we're talking about dynamic polymorphism. In order for this polymorphism to take shape, this has to be both compiled and run. Okay, so you don't have classes anymore because at runtime, right? Remember, all of your classes turn into what? Instance. Okay, so class is a blueprint, whereas instance is that three-dimensional house you built, right? This is the analogy that I gave you 2 weeks ago. So that said, access everything that point has, including its protected members, X and Y, and access to its public methods. So this is the assessor method that has that's really responsible for computing the area of this point, which is 0. Point has no area. And circle has an area that is defined by radius square times pi, right? All right. Any questions about this slide? Okay, so like right now we haven't really talked about polymorphism, right? This is just the beginning of the polymorphism, okay? And I'll explain this a little more. So we start up with this setup right here. Let's move on to the next page. So just to illustrate what's going on, let's pick the common, area of methods that we all have, right, in point and circle. As you can see, point is a one-dimensional dot, right? It's a Blumen's guide. So it doesn't really have an area. So we can say return 0. That's fine. Technically, you could say 0.0 because the return type is float. But if you don't do that, then there is implicit casting. This is a topic I believe I talked about earlier in the semester. Well, circle on the other hand, right? Since you're doing definition of your method that is part of your class, this is a class scope operator. Okay, this double colon here. So circle's area has another formulation. This is radius square, right, times pi, right? So pi is abbreviated or summarily equal to 3.14. So this is the circle area. The above two definitions, these are your methods definitions, right? Definition and declaration are totally different things. Declaration means the signature itself, the method signature. Definition means the logic included in it. So these definitions are very specific. Inheritance allows you to extend functionality created to create subtypes, but you're stuck with the base functionality, the base class. What does that mean? Well, there is really no in polymorphism here. By inheritance, you're stuck with the base functionality, the base class. So if circle were to be by itself, there's no inheritance. Then this is the area. However, if you say circle is a point by virtue of doing, this is a semicolon. Sorry, this is a colon and a public point. Right. So if you use this inheritance to create a class circle, yes, circle still has access to this pointer area, but other than that, it's really just relying on its own definition to carry this out. So there is no swapping of circle can use this area or this point area can use this area type of thing, right? So there's simply no polymorphisms yet. Subtype means subclass, okay? So circle in this case will be the subtype of point. So as you can see, child is referred to as sub, right? Child in OOP language. Super is usually referred to parent. And this word super carries into Java. So you see super, super dot, super one, right? Super is a pointer, okay, pointing to the parent. So that's where we are with this slides. Any questions about this slide? Okay, let's move on to the very next one. This is our example here. So carrying over from the previous slide, we have this point and this flow area that returns 0. And then we have this class circle that is a point inheriting a whole lot of stuff from point as well as having its own radius, and Boolean is circle. This is very important because in this particular what is this? Oh yeah, this is a constructor. We can see that we're saying this is circle, right? It's the passed in user defined variable that carries either Boolean true or false. If this is a circle, then you would set its circle, which is the private member of this. Actually, this is the public member of this class to that value. So when you instantiate this particular circle, you say this is circle true, then this is circle will be true. Okay. And then you do the same thing with R as well. And notice that this operator, which is the concept I went through, I think 3 weeks ago, this is that instance pointer. Okay. So in this case, that instance is circle, which means this is a pointer to that circle. Okay. So if circle occupies a memory, let's say, FA2, this THIS is a keyword that implicitly points to the memory address or has the memory address of this entire circle instance in memory. So you can always use this, right, to refer to itself. Alternatively, you don't have to use this because since you are defining everything inside this entire class, using this is kind of redundant. You can actually just leave it because it's understood, right? This R is actually this R here. This circle is the member circle, or it's circle member variable. So there's no need for that. The reason why you see this instead and with the arrow sign is for readability. A lot of times, you don't want to just just write what you think is correct. Sometimes you want to make it also readable, right, and understood by folks who will be co-reviewing your work or taking over your work in the future. So we add this to substantiate, right, the reason what these are. So it makes it a lot easier to kind of read it. Make sense so far? All right, and then what we have here is our full definition of area. And this area involves checking to see if this circle is true. So alternatively, you can write this as this if you want. I simplified it by not having it, but having this is fine as well. Okay, so if circle is true, then you return R squared 3.14. This gives you the circle's area, right? If not, you can return points area. And notice what I said earlier before, right? If you want to refer to your parent or superclasses area in Java, all you need to do is type super, right? Super dot area. But in C++, there's no such thing as a keyword. It's called super. You would have to physically, right, or manually declare the scope of this area, which is coming from point, not from circle. Make sense? So this is what you do. If this is circle, then return R squared times pi. If not, then you return point area. So this is kind of what is going on here. Again, there is no polymorphism, right? This is not assuming anything. I mean, circle is circle. And if you want to point to, hey, you want to call point area method, then you have to manually put in this point class scope in order to get to it. Make sense so far? Does anybody have any questions about this construction right here? Okay, this is all usual boring stuff, right? We haven't even gone to the exciting part yet, but it's important to understand the construction here so that we can make use of some of the examples to come. All right, let's move on to the next one. So this is circle and point object, and here we're going to do something fun. Let's look at how we instantiate, how we create, right? Just remember, this is our construction, right? So if we put everything in a main, which is your console application, this is what we're going to do. We're going to pound include circle and pound include points. So these are user-defined header files that you would have as part of your circle and point, but in the interest of time and brevity, there's so much screen real estate. Let's just assume, right? There's circle.h and also point.h in your system already. Okay, so now that you bring your libraries in, you can, inside your console application, this is your console, to start creating them. So the first thing I want to do is create a point, and I say my x and y is 1, 1. Okay, fine. This coordinate, and then you can do p dot x, p dot y. The reason why you can do that is both x and y are protected, right? So you can have access to it. Great. Point area is p dot area, and that's it. So this is all pretty straightforward. You would statically declare and instantiate an object on the stack. There is no dynamic memory allocation because there is no new. There's no delete, right? So this is fine. This is what I actually called the constructor that takes in both x and y coordinate in points. So if you go back to the previous definitions here, you can see point actually has that constructor right here that takes in x and y. So that's essentially what happens here, right? Okay, so far so good. We do the same thing with circle as well, right? So let me use a different color. So circle instantiation happens at here. This is saying this is R, right? And the second Boolean is called is circle. So you would set these two member variables to what they should be. One of them is 2 and the other one's true. Then what you can do is you can call the circle area by way of C dot area, right? This is going to give you 2 times 2 times what? 3.14, right? And C dot X, C dot Y, this is all good because both X and Y, they came from where? Point, right? Because when you instantiate your circle, your Cx and Cy should have gotten an X and Y, which are protected variable that gets passed in or passed down or subclassed into what's called a child class called circle. Okay, so you can kind of go back and see, hey, I didn't specify my X and Y, right? All I did was this, right? So what is my default X and Y? What is that, right? This is where you need to go back and check to see what the prior definition of this was. So for point, your X and Y assumes no default value. Hold on a second. Let's see, clear. Hold on, let me take a look. This is Y. Yeah. So what you're doing here is you're just creating point and circle, and there is no, and you know that class. So this class inherits on point, right? So what do you think if you were just to instantiate your circle, you know, by invoking this constructor right here? What do you think would be the X and Y value for, oops, I kept going back to the wrong. What do you think your X and Y would be? Anybody? No, stop going. So look at this, right? Your X and Y should be 0, 0, right? The reason is because, oh, never mind. I use, yeah, so when you instantiate your circle, you call it the circle constructor. And this circle constructor also inherits from your point instructor, right? This is scope operator. Okay, this is saying that while you make use of your user defined constructors, you would also at the same time want to invoke the points constructor with a 0, 0 in it. Okay, so by doing this, if I go back here, by doing this, your X and Y would have been set to X equals 0, Y equals 0, because there was that point 0, 0 right there. Make sense? So this happens actually one at a time. Circle gets created and then point, actually no, in that case, point, this is actually a very good segue here. So when you have a circle that inherits from a point, this is a circle. When you create that circle, your parent gets created first. This is the order of creation. And when point gets created, it will have invoked this user defined constructor that has 0 equals x and y equals 0 as the starting point. So your point 0 0 will be called, and then gets created, and then circle gets created after that. Right, that linkage happens after C is created. So you have establishes the inheritance here, and this will give you 0. This will give you 0, and this area will be r squared times pi, right? So r is 2, pi is 3.14. All right, any questions about this console application snippet? Yep. Okay, and the other thing that I want you to pay attention to is the has a relationship. Meanwhile, circle is a point, but a point has a x and y, right? So has a is a composition. Composition is purely used in communicating software architecture. It is not software inheritance. That has nothing to do with the is a relationship, okay? All right, any questions about this page? All right, let's differentiate the is a and has a relationship here. So is a is a inheritance, has a is a composition relationship in ORP. So with public inheritance, we guarantee that data members and methods are public in point. They stay public in circle. Protected in point stay protected in circle. Private in point stays private in circle. Okay. So private in circle means the circle doesn't have any access to it, period. Okay. It is private. So it actually doesn't even get to circle for any private data that point has, right? So this is kind of like what happens in Vegas stays in Vegas, and right, no one else inherits that information from the originating or emitting source, which is point. So this is what happens. Okay, now let's do something a little different because we've done this object instantiation for circle and for point. We can totally do this, right? This is dynamic memory allocations. Okay, so I just wanted to make it clear. This is a dynamic memory allocation. So in this dynamic memory allocation, we're creating an instance of point pointing to that new instance memory address. Okay, so far so good, right? We can totally do that. Point is a concrete class, so and it's not an abstract class where you can't instantiate it. So you can totally do this. Create a point object. Fine. Now, since point is also a since circle is a point, what you can do is in C++ and in C as well, you can create what's called a static, right? Reference type. This is P, and point to a dynamic type, which is new circle, right? So this is very curious. What does that mean? Well, because this P is also shared, right, with circle having information that are interoperable, not interoperable, only one way. What happens is you can create a generic P. This P could be reassigned, right, to a circle. The reason we can do that is because circle is okay, it's a point. So you can literally think circle is a point. And because circle is a point, you can use point, right? It's pointer pointing to a circle. That's what happens. So this is very important polymorphism. Okay. Well, right now we haven't activated that polymorphic mechanism yet because there is going to be some mechanisms, some keywords involved. But this is polymorphism, the beginning of polymorphism here, right? You can think of, hey, whenever I have a lot of inherited stuff, subclasses strewn all over the places in my code, and all of a sudden, what I can do is I can, just create a a parent class pointer, and have those pointer point to, maybe this subclass, that subclass, that subclass, so on and so forth. So this ability to point to these new location that similarly is not a point itself, but something that is rather is a, is the power of polymorphism, and this is the foundation that bores this concept, polymorphism. Okay, so this is called upcasting. The reason is simple because we're upcasting circle into this P. Yeah, so don't worry about downcasting after. It depends on where you look at it, right? But my overall question is, what happens if I do P arrow area, right? So P is a pointer, so you have to use the arrow. So you think this area would be the points area or circles area? Which is it? Anybody? Well, let's look at P. So what is P? Well, P is this, right? So if you do P area, that has to be point. Okay. So yes, if you answer circle, you're wrong. But you assume to be right. Okay, just hold off on this. Right now you're wrong, but you will be right later. So the answer is point. And this is what happens. Right? Let's use the next page as an illustration. By the way, we're moving very quickly here because there's only so much to illustrate. So when you do, this is example number 1, right? When you instantiate a copy of point, you say, hey, this P points to a point. Okay, fine, we can do that. And this involves your default constructor, right? Default constructor. So far, so good. When you do P area, yeah, this is called the P area. No questions about it, right? P, because P is the point. Now, the curious thing is, this is use case number 2. If you create a P and say this P is actually a circle, you can do that. This is called upcasting. And you do P area. And this still calls points area, right? And the reason is simple. The way how your software works, at least in C++, is when you invoke a method, this method has to coming from, right, this invokers class. So this invokers class is P, is point. So this X coming from area has nothing to do with circle, right? So this is a tricky part, okay? So if you answer circle, you're wrong, but we'll look at the extension later. Now, number 3, I can also forget about dynamic memory allocation. I can just do this is what we call static allocation, right? This means that whole circle is allocated on a stack, not on heap memory. So on a stack, you can say P point, okay, so P dot area, right? Because P is on the stack, so you do dot operator, right? There's no arrow. So this gives you points area still, right? Why? Well, because, I look at my static, right, type. So when this P was created, it's based off of this type, right? It's almost like this, right? Integer start P. So this P is an integer type, right? So P cannot be, string, right? A, B, C, and P cannot be true or false. That's Boolean, right? Because P is an integer. So same idea too, right? You look at the static type. The static type is pointing to a point. So when you do P dot point area, you're pointing points area and points area. So far, so good, right? So 1, 2, 3 cases. Now let's look at use case number 4. All right. So you create a circle on the stack, and then you say, hey, point, let me create a reference variable. So this P is a reference variable. Okay. This reference variable P of point is C. You can totally do that because C is A. Okay. This is a inherited point. Make sense? This is the reason why you can do that. Okay, fine. P dot area. Again, it still calls points area. Why is that? Well, because you gotta look at this dynamic type, right? This static type is point. So whatever method you're invoking, that method has to be of that type, inside that type, or of that type. Make sense? Not the other one. Okay. So 1, 2, 3, 4. Any questions about this 1, 2, 3, 4? Okay, the burning questions you have, right? You've been waiting for this moment. How can we make P area or this P dot area, right? Depending on whether P is allocated on a stack or on dynamically, to call circles area instead, right? I want to do that because this is, if you can't do it, this is polymorphism. Okay, this is polymorphism, right? How can, the question is how, right? And this is what we're gonna do. Let's go into the next page here, right? This is what we see. So it turns out that there's virtual keywords that you have to use. This thing calls the member and the method in a type that a pointer points to. Example, if you want to call circles area and not points area, then you use keywords virtual in where? In your parent. Okay, so in this point, if you were to say, hey, you can think of this virtual as a label. If you were to attach this virtual label and say, hey, this flow area, it's virtual, right? Virtual means does not exist. Virtual is also the same as what's called abstract, not non-existent, right? Not there, not concrete, right? So this means that this flow area could be anything, right? That's essentially what this keyword means. Therefore, when you apply virtual keywords on a method that are meant to be polymorphic, that method becomes polymorphic, right? And this is what happens. Let's say, without changing anything else, your point instantiation, new circles, all the same. Your decoration, your inheritance, all the same. The only difference being that you're adding this virtual in point. Then all of a sudden, P is a static type. We talked about this, right? Circle is a dynamic type. When you have polymorphism, right? When a method is polymorphic, that dynamic polymorphic type is assumed, right? So this means when you do P area, okay, this is printing circles area, okay? So you can kind of think of these virtual as there's actually inherent inside your C++ at runtime, what's called a virtual table, okay? This virtual table keeps track of all of the virtual functions or methods that you have here. And whenever you attach this virtual here, this is going to say, yeah, point, and there's a circle section here. There's a point section. This guy right here is virtual. So, and because this is virtual, when this area is called, we're going to redirect this to C area here. This is a virtual table. This is the infamous virtual table that only exists in C++. So you probably read something about virtual table in your textbook. Now, this virtual table does not exist in C because C is not OOP, right? It's only OOP languages. You may be wondering, does Java, which is also OOP, right, have virtual table? The answer is yes, right? Deep down. But these is the what's on the service what's beneath the service has all been obfuscated, so you don't see it. But yes, if you read Java books, there's virtual tables in there. You'll be able to get to it, depending on how Java works with polymorphism. So that said, adding a virtual keyword is very important. This makes that methods polymorphic, and you would do virtual keywords on parent classes. Okay, you don't put virtual in a subclass unless that subclass is meant to be used as a parent of another subclass. Does it make sense? Because you can have linear, you can have serial, you can also have multi inheritance in C++. Okay. All right, I'm going to pause right here. Any questions about this particular slide? Or any questions about this virtual keyword? By the way, virtual is all lowercase, okay? Don't misspell it because otherwise you're not going to be able to compile your code. All right, I also reckon that, let me see. Yeah, we still have 15 minutes before the top of the hours. Let's clear the drawing. questions. Do we need to involve any STL? Oh, standard template library? Oh, you don't have to. No, there's not. The virtual is there. It's a keyword, just like integer is baked in. It's a primitive. So this keyword is available free of charge. You don't have to pay for it. Okay. All right. Any other questions? All right. Let me clear this thing. Let's move. We only have two more slides. Look at that. All right. This is another example, a full example making use of virtual keywords. So let's take a look. Oops. Let's take a look. So this is your virtual area. So when we instantiate P against the P, right? This is basically using its own, right? Same object. When we call P area, this is called P's area, right? You can still do that, right? Even though this means abstract. Okay, I'm gonna make a super clear distinction here, okay? So having this virtual being abstract doesn't mean that entire class is abstract. Abstract in computer science means that it cannot be instantiated. It has to be implemented by something else, by somewhere else. That's not what I meant by abstract, okay? This virtual, you can think of, maybe abstract is a bad term. This virtual will just be virtual table. Okay, so you can think of this virtual as a keyword, as a placeholder, maybe as a label, as a sentinel value, that is attached to this point. But this point can still be instantiated, okay, at this point. So this does not make the entire class abstract. If you took Java before, abstract class cannot be instantiated. That's true. So abstract does not mean virtual. So that's use case number one. Use case number two is now we're going to do point, right? I pointed to a point equals new circle. We can do that because circle is a point. And when you do P area, you get circles area. Same thing, with static polymorphism. So this is not static polymorphism. This is allocating on a stack. This is dynamic. This is static. So circle C, okay, so you create an instance of it on a stack. You say, I'm going to create a reference. That is a C itself, which is fine because circle is a point. Then you do P dot area because P is a instance, right, on a stack. So P dot area, not P arrow. Again, this calls circles area because your method area is polymorphic in nature. Okay. So if it is polymorphic, that means skip it. Okay. That means there is a virtual table. You can think of this virtual table as a routing table and says, hey, if this P calls it an area and this area should have been point, let's look at the virtual table next. And this virtual table will be consulted and give you back a circles area, right? So another way of thinking about this virtual table is your address, right? USPS addressing system. You give it an address, right? And you slap an address on the envelope. You send it with the postage. Boom, that letter shows up, right, at someone else's footstep using that address. So it's really just a address, or you can think of it as redirection, a runtime redirection. Okay. All you need is that virtual keyword, right, in front of the method that you want to make it into a polymorphic in nature. Questions about this virtual keyword? This is an example right here. All right. This very last part is what we call pure virtual. Yes, there is virtualness on steroid. So I like talking about this a lot. It's called pure virtual. Pure virtual is a true abstraction. Okay, abstract. Okay. This actually makes your entire class with this pure virtualness in it abstract, which means this class is meant to be subclassed. It is not meant to be instantiated. Okay. This is an example where point now has this area that is completely pure virtual. Pure virtuals It's not a keyword. Okay. Virtual is a keyword, but pure virtual is not. To make it pure virtual, aside from it being a virtual, is to slap a equals 0 at the end of your method declaration. Okay. This means that, hey, this virtual method is to be inherited, is to be overwritten, is to be what? Implemented by someone else who subclass me, right? So this is an example. And here, this area has to be defined with some logic in it because you want to implement pure virtual method. Now, if there's no definition of this, your entire solution software is not going to be compiled. Okay, so there is that compilation logic that bakes in there. Whenever you see pure virtual, it has to be implemented somewhere. I believe this is a runtime behavior and not a compiler decision. So yes, yeah, you might not be able to compile it, but worst case is that you will compile it, but you won't be able to run it, which kind of sucks because that kind of wastes the time, right? You want the compiler to tell you that. So abstract class cannot be instantiated. This is very clear. This says, so if you have something like this, right, by virtue of having this pure virtual right here, by the way, this is virtual, but the second one is pure virtual, okay? They're two different things. So if you were to do point equals new point, can you do that on this point? Can you do that? Question mark. Yes or no? What do you think? Knowing that point is pure virtual, it's abstract. Can you instantiate a copy of your point dynamically like this? Yes, you cannot. Okay. You absolutely cannot do that. This is similar in Java, right? When you have an abstract class, you cannot instantiate it. Why will we have abstract class? Well, abstract class is there for the purpose of being inherited, period. It's for other people, right, who wish to inherit this parent class, to overwrite, right, its abstract method and to be instantiated, period. Okay. And the concept is similar to interface in Java, where you create an abstract interface that is meant to be inherited for the sake of, separating your code concerned, making sure all of the class, definitions and constants is into that interface, and anybody can inherit from it. Or in Java's term, they don't call it inherit, they call it implement. That is interface polymorphism. And there is also class polymorphism in Java. Again, we're talking about C++, so let's get back. So that's it. I have another demo that will illustrate the efficacy of this and how to do this more in your job in IDE in the next video. But let me pause right here. Any questions about this? Polymorphism, pure virtual. The telltale sign is that equals 0 right there. Question, where's virtual and pure virtual used in industry? In what applications? Virtual is used all the time to create polymorphism, right? So let's say if you have an application in banking where your software is a slew of accounts, right? So as you can imagine, in bank, there are multitude of account types. There's CD account, right? There is checking account. There's savings account, right? There's different types of maybe a loan account, right? So every single one of these account assumes a different shapes and behavior, but you can create what's called account parent class, right? And it is a virtual, it has a lot of virtual methods, like, your deposit method, right? Or withdrawal method. This could be virtual. And depending on what your account is, there's a savings account, right? Or it could be another checking account, right? Every single account may have limitation, meaning you can always deposit money, right, into your CD account, right? But CD is fixed, right? Meaning you don't take money out of it for an extended period of time. If you do, you get penalties, but you get higher interest rate. You guys know what CD is, right? Yeah, and then that withdrawal right there, right, is subject to your maturity of your CD, and that withdrawal is a polymorphic. So it could be virtual inside the account, implement outside. All right. Pure virtual, it's really for the sake of making sure that for sure, hey, all of your child classes, they all need to implement their own. Then you can actually make that pure virtual. Okay. So it depends on use cases. This is just one of the many that I can give you. But as you grow senior and more senior in this field, yeah, you're gonna end up and you'll participate in software design. You can see why certain things are abstract and why they had to be abstract to begin with to glean more insights into it. Yeah, there is a lot of YouTube videos out there that talks about pure virtual, and why we're using virtuals. I don't have those videos in front of me, but you can go out there and search for it and ask me any questions you may have. Question: if Circle did not define name function and you did point p new circle, and if you call p name, would it be p name instead? Let me think. Yeah, if you don't define name, wait. Yeah, so assuming name is already in P, I don't know if I understand the question. So let's say point, right, has a name method in it. And then you have circle, which is inherited from point. And then you call, right? So, and then you do P point, P equals new circle. Okay, that's fine. So when you do P name, um, if circle did not define a name, I see what you're saying. But are you talking about virtual name? Okay, virtual name. Um, I believe you get an error in this case. So what is virtual has to be defined. Has to be. This is has to be. Okay, you can't just leave it there. Because what happens is there's that virtual table. The moment that you slap this virtual keyword to it, it's going to say point has a name. And when point's name is called, go to see circle's name, right? And if you don't have the name defined here, this interaction is going to break. Okay, this is going to lead to error. Yeah, I believe it's a pretty bad error. In that case, your code is just going to crash. All right, but I think there's a chance that your compiler might be able to pick this up because it's pretty basic. If we see a virtual, you'll ensure your subclass virtual polymorphic method is implemented. So this could be a compile time determination. So that's pure virtual in its upshot.